Hello, welcome to another session on math for data sciences. So we have been looking at continuous uniform distribution in the previous session, and we looked at how we can define the probability density function. We got the probability density function up as 1 upon b minus a, and if you remember, we got this value by using the property that the sum of all probability across any PDF should be equal to 1, for which we computed the area under the PDF for the uniform distribution and equated the area as equal to 1. So using this, we were able to derive the height of this PDF as 1 upon b minus a, which is the constant PDF for a uniform distribution across the whole X range. Then we also looked at the cumulative distribution function, which gives the probability of the random variable to take a value less than equal to some x value, and we got it as x minus a upon the range of the distribution again, which is b minus a. And we looked at calculating the value of the CDF at the end value, right end value b gives 1 because all the values are less than equal to b. Therefore, the probability of getting a value less than equal to b is 1. And similarly, the value of the CDF at the starting value a is actually equal to 0 because there is no probability of getting an x value less than a. Next, we also derived the mean and variance for the uniform distribution. So the mean was computed as the integral of product of x with the PDF fx with respect to x in the whole x range, while the variance was computed as the difference between the second movement of x and the square of the mean, which is computed above. And this came out to be p minus a whole square upon 12. So these are the metrics for the continuous uniform distribution which we have looked till now. Now moving further, we want to see how the PDF and CDF are actually related to each other. So what does PDF actually represents? So PDF is kind of a probability for x at a particular x value. Now, if you remember, for a continuous distribution, the probability of x, the random variable x, taking an exact value is approximately equal to 0. So what we do to get the PDF, we actually look at a very small interval where this curve could be considered a constant value. So if we see this particular curve, we'll see that at each value of x, the value of this PDF is actually changing for each x. But if we keep on decreasing this small delta x and we tend it to 0, like we make it very, very small, then for that particular small range, the value of the probability should be equal for different values of x. So we are looking at a very small part of this particular curve where the value of probability is actually constant. Now to get that, we basically denote the PDF using a small f like we have seen before. So what we do, we calculate the limit for delta x tending to 0, and to calculate the probability at that point, we use the CDF instead of, because we already know CDF here, we are trying to derive the PDF from CDF. So we calculate p x plus delta x, so x plus delta x minus p x less than equal to x divided by delta x. So I'll just go through it in a more granular manner. So what we are doing here is, let's say we are trying to magnify this here, this particular part of the curve. So let us say this is the magnified version where this is x plus delta x and this is x. So these are the values of on the x axis. Now if we are computing all the probabilities less than x plus delta x, we are essentially calculating the area to the left of this particular vertical line, and the probability of x less than equal to small x, we are calculating the probability to the left of this particular line. Now when we subtract them, what we are getting? We are getting the probability in this particular region, which is the required probability here, and therefore the numerator is the total probability for P x less than equal to x plus delta x. Now, since we are calculating the probability for multiple values of x and whose range of these x values is delta x, to get a probability at a point, we need to divide all the probabilities, sum of all the probabilities for delta x by delta x, so that we get the probability at a particular point, and therefore we use delta x in the denominator here. Now, once we have done that, this limit represents nothing but, so if we can write it in terms of the CDF now, this becomes f x plus delta x minus fx. So capital F represents the CDF, delta x. Now this is a general form of a derivative of capital Fx with respect to x. So what we have seen here, PDF is nothing but the derivative of the CDF with respect to the random variable itself. Another way to look at it is, if you remember, we were calculating Fx CDF Px less than equal to x as the integral of Fx with respect to dx from the min value, or you can call it minus infinity, let's say, to x, any x value. So we are integrating the PDF to get the CDF, and therefore we just need to differentiate the CDF to get the PDF back, because we know derivative is the opposite of integration. And this is one more way to get to this particular expression here. So now we have seen here that PDF can be obtained from CDF of any random variable or any distribution by simply differentiating the CDF with respect to the same random variable. Now let us try to get the PDF from CDF for a uniform distribution AB. So once again, we know the CDF already, which was derived in the previous session as x minus a upon b minus a. Now if we differentiate this expression with respect to x, we'll be getting 1 upon, so we'll do dfx upon dx, which is equal to small fx. This is the PDF, and this is nothing but 1 upon b minus a, because derivative of x, so dx upon dx is 1, and b minus a is a constant, so we can bring it out, and the derivative of a constant, so dA upon dx is anyway 0, because derivative of a constant is 0, and therefore we get the required PDF 1 upon b minus a. And if you remember, this is also the PDF which we had seen earlier for the uniform distribution. So this is how we can get PDF from the CDF of the distribution. Now moving further, we'll be looking at another new concept here. So we'll be looking at something called quantile function, or we can also call it percentile calculations. So let us say we have a uniform distribution again from A to B, and let's say we want to calculate the 60th percentile. So we call it Q60 percentile for the distribution. So what does we mean by 60th percentile? Let us look at an example. Let's say there are 1,000 students who took an exam, and there's a person called George, and he got, let's say he got 90th percentile in the exam. What this means is, this means he scored better than 90% of the students. So he scored better than 90% of the students, which means the probability of George score x to be less than equal to, so the probability of the random variable, so this is a random variable representing score in the exam. So this is not George score, but a random variable representing score in the exam. And if this is equal to less than equal to George score is actually equal to 0.9. The probability of any score being less than equal to George score is 0.9 if we select randomly any score from these 1000 students here. So what this also means is that 900 students scored less than George, and therefore the probability of any score being selected which is less than George is equal to 0.9. So what would Q60 now mean here? This would mean Px less than equal to Q60 should be equal to 0.6, since this is a 60th percentile score, which means 60% of the scores are less than this score, and therefore the probability of the random variable taking less than this score is equal to 0.6. So this is nothing but f of Q60 is equal to 0.6. So this is the CDF, because CDF represents the probability of x being less than equal to x. Therefore, now we simply use the definition which we earlier derived for PDF, which was x minus a upon b minus a. This is equal to 0.6, and therefore we can get Q60 as 0.6 b minus a plus a. Now this can be obviously generalized as the pth percentile as p b minus a plus a. So this is the function using which we can calculate the percentiles for any random variable. In this case, for a uniform distribution, we derive the given expression. So once again, like we don't have to really memorize or learn anything here. This is just to show how we can calculate any percentile for any distribution in general. Now, once we have done that, let us try to calculate the median of this distribution. So we all know how a median is calculated. Median is nothing but the middle score of the distribution. Now, just by looking at a uniform distribution, we already know if the uniform distribution ranges from A to B, then the middle score would be the average of the two, which is A plus B upon 2. But we'll see how we can derive that here. Now, by middle score, we means it is the 50th percentile score, which means half of the scores should be less than the median. So Px less than equal to median should be equal to 0.5. Therefore, median minus A upon B minus A is 0.5. Therefore, median could be calculated as 0.5 B minus A plus A, which is 0.5 B plus A, which is the required expression, which is the middle value as we saw from the graph above. So this is how we can calculate the quantiles and the median value for any distribution. Now, moving further, another related concept is calculating the first and the second quartile value. So Q1 and Q3. This is called the first quartile value, and this is called the third quartile value. And Q1 is nothing but the 25th percentile value, while Q3 is 75th percentile value. So now that we already know how to calculate the percentile values, we can easily calculate Q1, Px less than equal to Q1 as 0.25. Therefore, Q1 is equal to A plus 0.25 B minus A, which is 0.25 B plus 0.75 A. Similarly, Q3 is A plus 0.75 B minus A, which is nothing but 0.75 B plus 0.25 A. So this is how we can calculate the quartiles, the first and the third quartile for any distribution. And just for the sake of completeness, the second quartile is nothing but it is equal to the median of the distribution. So which is very intuitive, since we are calculating the we would calculate the value which is more than 50% of the values here. So this is how we calculate the quartiles for any distribution. Now another term which is often used to calculate the, so it's a measure of spread, and it is called IQR of the distribution. So IQR of the distribution is nothing but the interquartile range of the distribution, and it is computed as Q3 minus Q1. So if we calculate it for the above distribution, we can simply put the values here: 0.75b plus 0.25a minus 0.25b minus 0.75a, which comes out to be 0.5b minus 0.5a, which is b minus a upon 2. So for a uniform distribution, if we look at the graph, this is the uniform distribution from A to B. The middle value, median, would lie here. The Q1 value would lie here. In this, so Q1 is nothing but the center value of A and M, and Q3 is the center value between M and B, and the interquartile range is computed as this particular value, which would again, due to uniformity for this particular kind of distribution, is same as the half of the total range, which is calculated as P minus A upon 2. So for uniform distribution, as I said earlier, this is one of the easiest one. Therefore, we are easily able to explain these various metrics which we have looked at. For further complex distribution now, we can simply use the same theory here, what we have seen for uniform distribution, and get the same metrics which we have seen here. So once again, for uniform distribution, the interquartile range is calculated as the difference between the third and the first quartile of the distribution. And this is the same way we would be looking at other distributions as well.